So far I've talked about small, but I haven't really talked about new phenomena that you observe because of smallness. And Feynman was acutely aware that when you make things small, quantum mechanics is going to play a role. Now, it turns out that the reason for that is that the length scale associated with, for example, an electron is very small indeed. It's on the angstrom scale. That's why electron microscopes can image with that resolution. And if you put something like an electron in a small enough box, then the size of the box begins to influence the energy of the electron itself. So if you take a slab of semiconductor, which typically has a pretty well-defined band gap, meaning that if you shine light on a semiconductor, ultraviolet light, it will then fluoresce somewhere in the visible. But if you then make the piece of semiconductor smaller and smaller and smaller, so this equation here is an equation for the energy of an electron in a box, eventually when you make it small enough, the size of the box will cause the allowed energy states of the electron to separate, to become large in energy. And so something that starts out fluorescing in the red, like these materials here, as you make the particles smaller and smaller, go to shorter and shorter wavelength fluorescence. So here, yellow, green, and blue. These are fluorescences generated by suspensions of quantum dots. Now, the question of what is small here has to do, you see in this formula, L the size of the box, and m the mass in this case of an electron. And the thing that decides whether a system of a given size L is small is the value of this constant here. This constant here is called Planck's constant. And it plays a central role in the scale of phenomena in quantum mechanics, and we will cover that in very great detail in Chapter 2.